All right, welcome back. Good to see everybody this morning. So we're on to the last of the new material for the first test today. So we finished up the elbow, wrist, and hand last time, and so now we're going to do kind of a space filler as far as the labs go. We're going to do joints. And so a lot of this stuff I've touched on some, but now we're going to do it in a little bit more detail. So for example, we talked about what joints are. So those are obviously the interaction of two or more bones. And then we talked a little bit about things like joint capsules, where capsules have two layers. There's the synovial membrane, there's the outer fibers layer, that kind of stuff. But again, we're going to hit that a little bit more specifically with this chapter. So before we talk about joints themselves, one of the things about joints is that there's a lot of connective tissue in joints, right? So if we think about the fibrous layer of a joint capsule, that's going to connect two bones, and so the tissue that does that is connective tissue. So we're going to start by talking about connective tissue in a little bit more depth, and then we'll get to the actual characteristics of the joints. So a lot of this stuff, the first, I think, 5 or 6 slides comes actually from chapter 4. So in PEPROF 202, the second half of this class, or the counterpart to this class, one of the things that we do is spend a decent amount of time talking about different types of tissue. So we talk about epithelial tissue, nervous tissue, etc., but we spend a lot of time talking about connective tissue as well. So since you haven't had that yet, I figured it was probably worth touching on. So as far as connective tissue goes, you can see that there are 4 classes. We're going to spend our time for now talking about the first 2. So there is connective tissue proper. And connective tissue proper, there are, broadly speaking, 2 categories of that. So there is loose connective tissue proper. And so loose is what we're really going to talk about in 202. But loose connective tissue proper, what that refers to is kind of a combination of the fibers that make it up. We're going to talk a lot about collagen. And so your loose connective tissue has relatively few collagen fibers and a lot of fluid in it. So the classic example there is, it's called areolar connective tissue, which is what surrounds, for example, your blood vessels are kind of packed in areolar connective tissue, and a number of other organs. The basal lamina, when we talked about the muscle cell, if you see that diagram, if you've seen that diagram in the anatomy app, that's a type of areolar connective tissue, or that is areolar connective tissue. So that's loose connective tissue. The other category of connective tissue proper is dense. And so dense is going to include things like ligaments, tendons, and fascia. So that's where we're going to spend our time for right now, is on the dense connective tissue. As an aside, connective tissue proper also includes adipose or fat tissue. That's a type of loose connective tissue because it's mostly cells, in that case adipocytes. And then obviously we're going to talk about cartilage some. So as far as the functions of connective tissue, some of the things that we're going to talk about apply here, so binding and supporting. So what do ligaments do? What's their job? Anybody remember? What 2 things do they connect? Bone to bone or muscle to bone? Bone to bone, good, yep. So remember that ligaments connect bones to bones. And if I injure a ligament, what is that called? Sprain or strain? Ooh, other one. Sprain. So injuries to ligaments or joint capsules are sprains, SP. And then damage to muscles or tendons is called a strain, ST. So somebody has a hamstring strain or an ACL sprain. So that's how those 2 work. So obviously both ligaments and tendons bind and support. Ligaments hold bones together. Joint capsules hold bones together. As far as protection, I guess you could argue that ligaments protect the joint in that they provide that static stabilization. They keep those 2 bones in line with each other. Insulation is really fat, which again is a type of loose connective tissue. Storing fuel is also fat. Now that said, some of the types of loose connective tissue can store some carbohydrates, but in general it's fat. And then transporting substances obviously applies to blood. All right, so in terms of looking at connective tissue under the microscope, looking at it more closely, so there's 3 main elements to connective tissue, whether we're talking about loose or dense. And the 3 main elements that you can see there are the ground substance, fibers, and cells. So the ground substance is where we'll start, and as the slide says, that's the space between. That's essentially the fluid, the extracellular fluid. So anything extra is outside of, so extracellular fluid is fluid outside of a cell. So the ground substance then is a bunch of fluid that the cells float around in and that the fibers float around in. Okay? So in terms of what's in that fluid, what's in the ground substance that takes up the space between the cells and the fibers, well, there are a few things in there. The first is obviously fluid. The second one that you can see on there are adhesion proteins. So anything that's adhesive is sticky. And so adhesion proteins are proteins that allow the cells in that ground substance to stick to that extracellular matrix and stick to each other. So they allow things like the fibroblasts to stick to the collagen fibers. They allow the adipocytes, the fat, depending on which type of tissue we're talking about, if there's adipocytes out there, they allow it to basically stick to the scaffolding, maybe the reticular fibers in that particular connective tissue. So adhesion proteins help the cells and the fibers stick. But what we're more concerned with are our proteoglycans. So what are those? They're a combination of proteins and sugars. So proteo obviously is protein. Glycans sounds like glycogen or glucose, and so those are sugars. And so they're these combination molecules that are part protein. Effectively, they have a protein core kind of down the middle, and then they have these long strings of sugars. So they're more technical term, polysaccharides. So poly is a lot of, saccharide or sugar. So they have these long strings of polysaccharides, these long strings of sugars that extend from this protein core. And so the most important of those are our glucosaminoglycans, or GAGs, which is how I'll refer to them the rest of the time. So the GAGs are proteoglycans. They are a combination protein sugar. And what they do, so those polysaccharides, the sugars that extend off of those protein cores, are negatively charged. Why does that matter? The reason that matters is that helps those long strings of carbohydrates hang on to or attract water. So the more glucosaminoglycans a particular type of tissue has, the better that it holds water. And so most of your connective tissues, especially like when we talk about cartilage is going to have lots and lots of water, so it has lots and lots of GAGs. And so depending on the number of GAGs, the more of them we have, the more water we can hold. And so we end up, the combination of those sugars and waters, you end up with a more viscous or thicker ground substance. The fewer GAGs you have, the thinner the ground substance is effectively. In addition to that, they also hang on to positively charged ions, so things like calcium or sodium as well. And so then those ions can also pull water with them. So GAGs, the thing to know is that they attract water and they hang on to water. So the content of GAGs in any particular connective tissue determines the water content. So that's why they're important. In terms of the connective tissue fibers. So when we talk about fibers, I'm primarily talking about collagen for our purposes. So you can see collagen fibers on there. So on this particular diagram, so what you're looking at is kind of a generic connective tissue schematic. So what you've got on there is, so here's your collagen fibers, the thicker ones, and then you've got elastic and reticular fibers, which we'll get to. The elastic fibers are kind of this yellowish-orange color. We'll talk about those in a second. So as far as collagen fibers go, there are as many as 28 different kinds of collagen that the human body makes. So we make a lot of different kinds of it. What makes one type of collagen different from another, you might ask? And the answer is the protein sequence. So collagen is a type of protein, and proteins are made up of amino acids. So amino acids are the building blocks for proteins. And as far as the structure of collagen goes, it has a triple helix. So if you think back to what you learned about DNA, remember DNA is a double helix. You have the nucleic acids running next to each other and linked. In the case of your collagen, you have 3 proteins running close to each other and then kind of twisted around each other. So there's a triple helix to them. So the particular sequence of amino acids that makes up the protein determines the type of collagen. And that then gives the collagen its structural characteristics. So really, in the course of this class and the next one, we're only going to talk about 3 different types of collagen. So the first is type 1, pretty straightforward. So the collagen that you see there pictured, or that is depicted here. So this is your type 1 collagen. And what it is fairly thick collagen. So it is really dense, really high tensile strength, meaning that you can pull it apart and it's really resistant to being pulled apart. So it's this really, really strong fiber. That's as opposed to your type 2 collagen. Type 2 collagen is more of a scaffolding. So we see type 2 collagen pretty prevalent in hyaline cartilage, which lines the ends of your long bones. And so it sort of forms a scaffolding for the extracellular matrix. So that's type 2. And then type 3 collagen is a little bit stretchier than type 1, a little more elastic than type 1. And so where those come in, so your tendons and ligaments are primarily type 1 collagen, especially your tendons. Your cartilage has a lot of type 2 collagen, a lot of scaffolding for the extracellular matrix. And then type 3 collagen, we'll talk about actually as it comes to the heart. Your heart adapts as you age, unfortunately, generally negatively. The type of collagen in the heart switches from type 3, the more elastic type of collagen, to type 1, the less elastic type, with aging. And that's one of the things that causes your heart rate to decrease with age, or not heart rate, but cardiac output to decrease with age, is because of that shift in collagen types. So those are your collagen fibers. Elastic fibers are, as you would expect, they're kind of rubber band-like. So the elastic fibers are capable of being stretched and returning back to their original length. So elastic fibers then, or a way to think about the interaction between collagen and elastic fibers, collagen fibers give tendons their strength. Your tendons are really dense. They have lots of strength. They can resist lots of pulling apart, lots of tension. And then what actually causes them to snap back to their original configuration after you release the tension, the primary thing causing that snapback, are the elastic fibers. And then the difference between tendons and ligaments, one of the differences is that your ligaments actually have more elastic fibers than the tendons do, which seems counterintuitive because you think tendons connect muscles to bones, and so you'd want those to be good and springy, but actually they're really, really dense, as opposed to the ligaments are actually fairly springy. So for example, if you buckle your knee toward the midline and allow it to come back laterally, so there's some springiness in it. If you ever test ligaments, if you kind of pull on them, pull on somebody's joint to their end range of motion, there's some springiness there at the end range because of those elastic fibers. Reticular fibers we're not going to worry about for now. Those come into play when we talk about like abdominal organs like the spleen, or when we talk about the scaffolding around blood vessels. Then reticular fibers are important, but not for now. All right, so cells found in connective tissue. So the end of the word, I guess that counts as the suffix, tells you something about the cell. And the first part of the word also tells you something about the cell. So essentially the first part of the word tells you what type of cell we're talking about. So anything chondro is cartilage. Anything osteo is bone. Myo is muscle. So chondro, cartilage. Osteo, bone. Myo, muscle. And then the other one that we're going to talk about, actually the one we're going to talk about the most, is a fibroblast. So fibro, those are just connective tissue cells. They're not anything specific. Look, let's think about it this way. Fibroblasts make fibers. So anything fibro makes fibers, so they make collagen, is I guess the most important thing I want you to know. So as far as blasts go, those are your immature cells. So a chondroblast is an immature cartilage cell. A chondrocyte, so anything that's a cyte, is a mature cell, so it's grown up. And an important difference between the two is that the blasts are much more capable of dividing. So blasts can make copies of themselves, so they can proliferate and make copies, and then those copies of themselves can play a really important role in tissue repair or tissue growth. The other thing to know is that the blasts are primarily responsible for creating that extracellular matrix. So when you're growing, before you reach skeletal maturity, when your cartilage is changing, when your bones are growing, all those kinds of things, it's the blasts that are generating most of the collagen to lay down that new bone, to lay down that new cartilage. So the blasts generate the extracellular matrix. They make the collagen that is going to provide, or that is going to then become a ligament, become a tendon, become cartilage. So the blasts make collagen. The cytes can make collagen, the mature cells, but they just can't make very much. So once these cells are all grown up, they can repair the extracellular matrix, they can repair damaged collagen fibers. They just have a lower capacity to do so than the younger cells, than the blasts. So as they get old and mature, they're basically less active. They're not as good at making new copies of themselves, and they can't make as many proteins. So they're good at maintaining the status quo when they're grown up, but they're not as good at sort of fixing big damage, if you will. It's kind of one of the things where this is important. So as far as other cell types found in connective tissue, so there's fat cells, depending on which type of connective tissue we're talking about. In general, things like tendons and ligaments don't have fat in them, so they are primarily fibers. White blood cells will come in if there's damage. So sometimes you'll see white blood cells, like in a tendonitis. If the tendon has been inflamed for a while, white blood cells may come in there. Mast cells, there's a little mast cell on here somewhere. There he is, the green one. Mast cells are actually important in primarily in areolar connective tissue. They sort of serve as these guardians when there's tissue damage. They cause the immune system, they attract the immune system cells, they cause vasodilation, they cause your capillaries to be leaky, all those kinds of things. So they basically initiate the inflammatory response is the job of the mast cells. And then macrophages are your big eaters. There's a macrophage up here. And so macrophages, what they do is they'll become important in some of the stuff we talk about. They clean up damaged tissue. Right, so if you've got damaged collagen and the collagen fibers are just kind of waving, and we need to get rid of the old damaged ones and replace them with new ones, macrophages play a role in cleaning up the damaged fibers. All right. So as mentioned, connective tissue proper has two subtypes, loose and dense, and we're only going to talk about dense. So a subtype of dense is dense regular connective tissue. And so what does regular versus irregular refer to? So with dense regular connective tissue, it refers to the direction of the collagen fibers, of those type 1 fibers. So in dense regular tissue, the fibers all run the same direction. They're all in parallel to each other. And so we see that in tendons, in ligaments, and in fascia, most fascia. So, because I use fascia fairly broadly. So in most fascia, we see that regular arrangement. So an important thing to know about tendons and ligaments in particular is that they are poorly vascularized. So what does that mean? So that means that they have relatively limited blood supply. A tissue that has limited blood supply therefore has limited access to oxygen, and tissues that have limited access to oxygen are not very good at repairing themselves. In addition to that, they have a harder time getting the building blocks like the amino acids or the glucose molecules that they're going to need to repair themselves. So any tissue that has a poor blood supply is not very good at repairing itself. So if you damage cartilage, if you damage tendons and ligaments, they're not very good at repairing themselves. As opposed to bones, if you break a bone, you can heal a fracture in 4 to 6 weeks. It's typically pretty quick. But ligament injuries, tendon injuries can linger for a lot longer than that because of that lack of blood flow. So the way those are set up, and so as mentioned, the collagen fibers all run the same direction. And so this is the long head of biceps tendon. And so you can see the collagen fibers all run the same direction. That there's not a lot of extracellular matrix with any of these, so there's not a lot of fluid component to these. It is primarily collagen fibers in fairly large bundles and fibroblasts. So fibroblasts, again, immature fiber cells, if you will, that are going to generate, or the thing I want you to know about them, they make collagen molecules. And those collagen molecules, then we can repair our tendon if we need to. All right, that's as opposed to dense irregular, which is that the collagen fibers run a bunch of different directions. So we see dense irregular connective tissue in the case of that outer layer or more superficial layer of a joint capsule. So think about a joint like the shoulder, which can move in all 3 planes. And so if we only had the fibers running one direction, well, that's only going to protect us against, let's say, extension external rotation. But if the fibers run a bunch of different directions, well, that's going to some of the fibers will protect us against hyperextension, some will protect us against hyperabduction or hyperexternal rotation. So the fibers running in a bunch of different directions in an irregular arrangement helps then protect it against a number of different directional and tensile stresses. We also see some irregularity when we think about the layers of connective tissue around a muscle. So for example, the epimysium is irregular tissue. The fibers run in a bunch of different directions. Now, once it gets to the tendon, the fibers all run the same direction. But in the epi and paramycium in particular, you see the fibers running in a bunch of different directions. And then the last type there, elastic. So we'll talk about elastic later in the class. But elastic connective tissue has a high proportion of those elastic fibers. So lower proportion of collagen, much higher proportion of elastic fibers. So those are kind of your stretchier ligaments. And so we see those in the ligaments of the spine, particularly one on the posterior aspect of the vertebral canal, which is called the ligamentum flavum, or yellow ligament. And the reason it's yellow is because of the high proportion of those elastic fibers, so they're really stretchy. We also see those around large arteries like your aorta, the primary blood vessel, or the blood vessel leaving the heart. All right, so in terms of connective tissue characteristics, some of the same ones that we talked about with muscle. So the first one there is elasticity. So again, elasticity describes the ability of a tissue, or of any material, to return back to its original, to be deformed, to change shape, and return back to its original configuration. So oftentimes we think about elasticity in terms of something can be stretched and then return back to its original length, which is what happens with ligaments and tendons and muscles. But remember that elasticity can also refer to the ability to be compressed and come back to its original configuration, because that's going to be important with cartilage, and that's going to be important with bones as well. And then extensibility is the ability to be stretched. A couple other terms on there, so stress and strain. So stress is a force or a load, and then strain is the deformation, the change in shape that's caused by that stress. So, for example, your bones are also elastic, so they're not really stretchy per se, right? But they're capable of bearing a compressive load, and then they deform a little bit. So they actually, your bones bend a little bit, they have some give to them, which is good, because that helps absorb the shock of, so if you land really hard on one leg, your femur, your tibia will bow very, very slightly. It's not something you can see, but there's some bending in the bone that happens, right? So that stress, that impact of all that weight landing along the bone causes, and that compressive force, causes a strain, causes a deformation, change in shape in the bone, causes it to bend. And so we see the same thing with ligaments. As you pull them apart, so with ligaments and tendons, the primary stress is a tensile force pulling them apart, and then so the strain is they elongate. And where any of that matters, it is related to injuries. So one of the things that I didn't really highlight when I talked about the dense regular connective tissue, so both ligaments and tendons, is that type 1 collagen kind of has a wavy arrangement whenever it is not stretched, whenever there's no tension on it. And that's important because when you stretch a tendon, when you stretch a ligament, the first thing that happens is those little waves, and so I'm talking about here on this little stress strain curve, the first thing that happens is those little waves flatten out, okay? So in terms of the x and y axis here, so the stress, for now, we're talking about a tensile force. We're talking about pulling a tissue apart. So as we go up the y-axis, we're pulling our tendon apart harder and harder and harder, right? As we go over here toward the right on the x-axis, that's strain, that's the change in shape of the tissue as a result of the increased stress. So if we just stretch a tendon out just a little bit, those waves in collagen go flat. And then if we continue to apply more tensile force, so we can increase it to up to about 5% of its original resting length. If we apply more tensile force, you're going to get some stretching of those collagen fibers, but no damage to them. So that's the elastic range, or elastic region on this chart. So what that means is when you let go, when you release that tension, that tendon will snap back to its original length. So that's that elasticity, returning back to its original configuration. What happens if I continue to apply even more tensile force to that tendon or ligament, if I keep pulling it harder and harder and harder? Well, if we do that, then we're going to go past our elastic limit to what's referred to as the plastic region. So the plastic region is where we see a permanent change in the tissue. So plastic is permanent. So plastic region, permanent change in the tissue. So where this applies, and I'm actually going to switch from tendons to ligaments here. So let's think about something like some of the ligaments on the outside or on the lateral aspect of your ankle. Right? So you can probably gently roll your ankle, no problems. But if you step off a curb wrong and aren't able to correct with muscular contraction, what you're going to do is eventually stretch that ligament so much that you're going to cause a rupture between the bonds of some of those collagen molecules. And so when that happens, now that ligament, that ligament is lengthened. It's longer than it was at first. You've actually caused some micro tears. You've caused some permanent damage to that ligament. So that's your grade 1 sprain. So a grade 1 sprain, whether it's an ankle sprain, MCL sprain, etc., is an overstretching of the ligament and a tearing of some of the bonds between those collagen molecules. And the effect is that that ligament now is longer than it was before. Where that matters from a practical standpoint is now that joint is less stable than it was before. You get extra movement between the bones that you didn't have pre-injury. So now you get abnormal movement in the joint. Then, if we apply even more force, we start to get a partial tearing. So you tear some of the collagen fibers, but not all of them. And so now, with that partial tear of the ligament, we get even more range of motion, right? So we have extra looseness, extra laxity in the joint because of that. So grade 2 sprain, broadly speaking, is a partial tear. So grade 1 is kind of a microscopic tears or an overstretching. Grade 2 is a macroscopic damage, partial tear to the ligament. And then grade 3, where we get failure, is a full rupture of the ligament. So grade 3 sprain is you tore something. You tore a ligament, you tore the joint capsule. So that's where those come in. And so one of the important things about that, and we'll talk about this more than once, this concept of once a sprain, always a sprain. Once you stretch the ligament out, it doesn't go back to its original configuration. So muscles, if you rehab them, you make them stronger, you can change their resting length. You can lengthen it or shorten it. In the case of ligaments, once they're stretched out, they stay stretched out. And so now that joint is permanently less stable. And where that becomes obvious is oftentimes people who have dislocated a joint, so now you've got a rupture of at least one ligament, they're going to have continued laxity, right? So somebody that's dislocated their shoulder once has probably done it more than once. Similarly, if you sprained your ankle, you've probably done it more than once. Most people that have sprained their ankle once, like it just keeps happening, and then they develop what's called chronic ankle instability. Part of that's the ligaments, part of that's the muscles around the joint, and we'll get to that later. But one of the aspects of that ankle instability is those permanently lengthened ligaments and joint capsule there. Creep, the last thing on there, low intensity, long duration stretching or long duration tensile force in this case causes a permanent change in the tissue. So what we can do is stretch a ligament out right up to its elastic limit a little bit, and then we can do that for a long period of time. We can do it for 5 minutes, we can do it for 30 minutes, however long. And so by applying that low load, long duration, it has the effect of causing plastic or permanent changes. You're going to break some of those collagen, some of the bonds between the collagen molecules, and you're going to structurally lengthen that tissue. Why does that matter? If you've ever seen anybody after an ACL surgery, oftentimes they'll have what's called a flexion contracture, which is where they can't fully straighten their knee. And so one of the things that we'll do to fix that is to have them lie face down on a table, and you put like a 5-pound ankle weight on there and just have them lay there with their leg hanging off the table. And so what you're trying to do is induce this concept of creep. You have the low intensity stretch, and so you're trying to break some of those collagen bonds, right, to try to lengthen out that posterior part of the capsule. So that can be used therapeutically. It can also be bad, because if we all sit here like this all the time, you get some creep in the ligaments of the spine, and so then they become permanently stretched out. So that's also, it's not good at times, but we can use it therapeutically to be advantageous as well. All right, so tendons. So one thing on this picture, so it's titled Tendons, and I'm talking about tendons, but the picture is of a ligament. So not to confuse you, but it was the best graphic I could find because the arrangement's basically the same. So don't let it throw you that I'm talking about tendons, but there's a ligament on the picture. I know. So what do fibroblasts do? Again, they create, they synthesize, which means to make collagen. So they use their DNA, they use the instructions that they contain. They make proteins. The particular protein that they make is collagen. So they make something that's actually called procollagen, and then they secrete that outside of themselves. And then in that extracellular matrix, there are enzymes that are actually going to cause, so here's our little procollagen up here at the top. So there's your collagen molecule. It has little extensions on it, and there are enzymes in that extracellular fluid that will cleave those ends and attach one collagen molecule to another. And so there are gaps between them, and you can see those there. And so that gives collagen or tendons or ligaments, kind of a striped appearance under a microscope because of those little gaps there. But those are where these extensions are and where the collagen molecules are bonded to each other. So we're going to bond a bunch of those collagen molecules together in series, and so then we get our microfibril. We get a bunch of microfibrils together. We get a fibril. Get that to come back. And then we get a bunch of fibrils together, and now we have a collagen fiber. So between collagen fiber and the fibrils, actually looks a lot like a muscle fiber and the myofibrils. Remember, the myofibrils is where the actin and myosin are. They're the little tubes where the contractile proteins are. So the myofibrils are basically the same as the fibrils are in tendons and ligaments, except now it's just collagen, it's not actin and myosin. So then we end up with our collagen fibers. And so the arrangement, the interesting thing, I think, is that the arrangement is basically the same. So you have these little tubes that aggregate with a bunch of other little tubes and then make one big one. So now we have our collagen fiber here, which again, so we'll say it's analogous to muscle fiber. And then we're going to bunch several fibers together, which is similar to a fascicle in a muscle. And then we'll have a layer of connective tissue there. So this graphic and the one on the anatomy app are very similar, but a little bit different. The differences don't really matter practically. But one of the things on the anatomy app, it talks a lot, or there are things that mention primary, secondary, and tertiary bundles. So if we look at the tendon depiction, here. So there's our generic tendon. And so if you look at it, so you're going to have your collagen fibers up here. And then if we rotate it a little bit, then we're going to have our primary bundles there. And then we get a little bit bigger. So we gather our primary bundles into secondary bundles. And then we end up with tertiary bundles. And then you've got layers of connective tissue around them. So, and the two layers of connective tissue in a tendon, the endotendon is going to wrap around the collagen fibers. So just like the endomysium wraps around individual muscle cells, the endotendon wraps around collagen fibers. And just like the epimysium wraps around an entire muscle, the epitendon is a layer of irregular connective tissue that wraps around an entire tendon. All right. So that's tendons and ligaments. Cartilage, similar arrangement, because again, it's still connective tissue. So we still got blasts, we still got a lot of extracellular matrix. So generally speaking, cartilage is avascular. So again, vascularity describes blood supply. So a tissue that is avascular doesn't have a blood supply. And again, why does that matter? Well, a tissue that doesn't have a blood supply is not very good at repairing itself. Again, it can't get oxygen to generate ATP, to generate energy, because we need energy to build things. But in addition to that, we also have to get the building blocks. We have to get the amino acids, we have to get the glucose, etc. And so if a tissue is avascular, we're not very good at getting those things. Lots of GAGs. So again, those are those proteoglycans that retain water. So whereas tendons and ligaments have relatively low water content, they're basically all collagen or elastic fibers. In the case of our cartilage, it's mostly water, especially when we're talking about hyaline cartilage. So they have a really high water content. So one of the things to know about cartilage as well, so mature chondrocytes, which is kind of redundant because chondrocytes, again, are mature cells, have a limited ability to repair the extracellular matrix. That's what ECM is. So especially when we think about something like hyaline cartilage, and I'll skip ahead a little bit. So what hyaline cartilage is it's the most abundant cartilage in the body. So it includes things like, as you can see there, your this cartilage that connects your ribs to your sternum, so the costal cartilage. But where we're going to talk about it primarily is in a special type of hyaline cartilage. It's called articular cartilage. And anything, again, articulation is a joint. So articular cartilage, again, is a type of hyaline cartilage. But basically, it's hyaline cartilage that lines the ends of long bones. And so it'll line, for example, the humeral head. We talked about the anatomical neck of the humerus, and that was where the hyaline cartilage ends. The glenoid cavity is lined by articular hyaline cartilage. So what that cartilage does a couple things. The first is it cushions impact between the bones. So it depends on which joint we're talking about. That hyaline cartilage may be like 1 to 4 millimeters thick, or in the case of the hip, it's more like 7 millimeters thick. So the more compressive forces there are, the thicker the hyaline cartilage is. So it absorbs those compressive forces, but in addition to that, it helps those two bones slide on each other. So an interesting stat I found was that two bones lined in articular cartilage sliding on each other, the coefficient of friction, meaning how slippery it is 5 to 20 times higher in hyaline cartilage than it is of ice sliding on ice. So you get really, really slippery, which is good. We don't want bones dragging on each other. That's going to cause inflammation and pain. That would be bad. So that's our hyaline cartilage. So in terms of losing the ability to divide, what happens is, and so this is a picture close up of hyaline cartilage. So you have your little chondrocytes, your mature cartilage cells, and then as you can see, all this is the extracellular matrix. It's mostly type 2 collagen out here and lots of water. So anytime you compress that cartilage, so when I'm standing or running or jumping or those kinds of things, we're going to get repetitive compression of the cartilage. You're going to damage some of those collagen fibers, whether it's type 1 or type 2. And so there's this constant repair that has to go on. And so your chondrocytes, the mature cartilage cells, simply can't make cartilage very fast, or can't make collagen very quickly. And they can't make very much of it. And so once you've matured, your collagen isn't very good at repairing itself. And why that matters is that's an important thing that leads you to eventually develop osteoarthritis, where you get inflammation inside the joint because of the wearing down of hyaline cartilage. So one of the reasons that happens is because those chondrocytes can't divide very effectively. Rarely can they divide. And so since they can't make more of themselves and they can't produce very much collagen, they're not very good at repairing that extracellular matrix. The other thing is, as you age, those chondrocytes can't produce very many GAGs, the things that retain water. And again, most of this out here is water. And so if we can't produce very many GAGs, our cartilage becomes less fluid with age, so it has a lower water content, and so it's easier to wear it down. And not only do they not produce very many, but they're also smaller. So again, lower water content, easier to wear it down. The other thing, so if those chondrocytes don't have a blood supply, how do they survive? Because they still get the nutrients they need, but where do they get them from? Anybody got a guess? It's a hard question. I probably didn't give you enough information to know the answer. The answer is the synovial fluid. So inside of a joint, you have fluid, synovial fluid, that both lubricates the joint, but also, as the fluid moves around, helps get oxygen, helps get proteins, or amino acids, to those cells. So as you move a joint, that squishes your synovial fluid around. And that movement of synovial fluid helps deliver the nutrients that the chondrocytes need in order to continue to survive and to continue to synthesize what little collagen they're able to do. So if you don't move, so like when a joint is immobilized for a long period of time, those chondrocytes in there, because you're not moving around, don't get a very good don't get a very good oxygen supply, don't get all the nutrients that they need, and so you're going to get some damage to the cartilage as a result of that. So, you always see those things about how we're made to move and all of that, and there is obviously some truth to that, even as it relates to cartilage, because moving within limits keeps your cartilage healthy. Now, obviously, if you move too much, you run 100-mile races, that's probably going to do more damage than it's going to do repair, or more harm than good, potentially. But that movement is important for getting those nutrients into those chondrocytes. And then, so that's hyaline cartilage. Elastic cartilage, so what do I want you to know? Hyaline cartilage, I'm going to use it interchangeably with articular cartilage, because again, articular cartilage is a type of hyaline cartilage. So know that hyaline cartilage lines the ends of long bones, cushions them from impact, causes them to slide on each other. Elastic cartilage we're not going to talk about, because we'll deal with it later or in the other class. But fibrocartilage is the other type I want you to know about. So fibrocartilage is similar to hyaline cartilage, except that there's a lot more type 1 collagen. Effectively, there's a lot lower water content. So remember out here, whoops. So remember out here, there's all this water content and fibers, but your fibrocartilage, you got some little chondrocytes. If I can get my mouse to come back, you got some little chondrocytes here, but lots and lots and lots of fibers. So fibrocartilage is a lot more dense. So fibrocartilage we see in places where we need lots of shock absorption. So we see fibrocartilage in the spine. So it's the intervertebral discs, the outer portion of those is fibrocartilage. Where we've talked about fibrocartilage so far in this class, the glenoid labrum, remember that is a ring of cartilage that lines the glenoid and helps both provide cushioning, but also provide some proprioceptive feedback where your arm is in space. That glenoid labrum is fibrocartilage. So we've seen that. There's a fibrocartilage disc in your SC joint that cushions between the clavicle and the sternum. So surprisingly, there's a disc there. When people think about fibrocartilage, other than the spine, they usually think about the menisci of the knee. So people are familiar, you probably know somebody or you yourself may have torn your meniscus. The menisci are these wedges of fibrocartilage that sit between the femur and the tibia, and their primary job is to absorb impact between those two structures. So that's fibrocartilage. All right. So, because the next time will be extra short if I keep going. So let's just leave off for there for today, and then we'll talk about joint classifications and stuff on Wednesday. So as mentioned in the email, the plan for the week is to do joints today, Wednesday. Thursday, we'll go over all the bones, bony landmarks, and muscles and stuff in lab. If you want to come, again, you don't have to, but if you'd like to come, that's what we're going to do. And then Friday, because the attendance is usually pretty low, which actually works out well here, we're going to play Jeopardy. And so that'll be a good review game for you. So Friday should be fun and help prepare you for the test on Monday. So yeah, so we'll see you on Wednesday.